But before we begin, are there any questions from previous time?
Yeah, I did have some issues with the L square integral functions. I did not understand it properly.
Okay, so L squared means that if I have a function, say phi of x, L squared means that if I take its complex conjugate and multiply it with itself, then I am taking the modulus square of that function, right?
Mm-hmm.
And suppose I am integrating now within some domain, and a lot of times that domain is going to be the real line. So say minus a to plus b, or a to plus a to b, right? So because if this integral does not diverge, that it's less than infinity, then we call it an L squared integrable function. As simple as that.
Oh, that's actually pretty simple. I
Yeah,
see. Got it.
yeah. It
Thanks,
just
sir.
generalizes the idea that when we have a vector, we define the norm of the vector to be the dot product of the vector with itself, and then we take the square root, right? So so this is basically the this just because there's a square here, right? And there's a square here, and that's the L2, the 2 in L2 stands for. I think there are other technical stuffs that mathematicians worry about, that psi of x cannot have, I think, an infinite, discontinuity. It can have discontinuity, but not an infinite discontinuity. And also, it cannot have an infinite number of discontinuities. And if you look at the L squared definition in a math book, it actually refers to not just a function, but an equivalence class of functions. And this has to do with the kind of the Lebesgue measure. So for example, suppose I take an L square function. Well, suppose, a function that looks like this. So, if I square, basically the area under the curve is going to be finite, right? But now just let's consider a function which, say, at this point has a singularity. Okay, so at this point it jumps like that. So does that change the integration under the curve? The area under the curve? No, it doesn't, right?
Mm-hmm.
So there could be another function where also there's a discontinuity, or at another point, another function which has a discontinuity at 3 points. So when we mean an L square integral function, we actually identify all these functions which differ from each other by a finite number of discontinuous points. Okay. But these are niceties that mathematicians worry about, right? Okay, we are not going to worry about that. Okay. Any more questions?
Does L2 integrable verify a L3 or L4 integrable on a higher dimension?
No, I mean, intuitively, I would say, yeah, maybe L3 integrable. If it's L3 integrable, it's probably going to be L3 integrable, but I'm not sure. Yeah. I mean, if you why is the L3 integrable, right? What is the mechanics require us to have L3 integrable functions? The answer.
Sir, we can't hear you.
Your sound is a bit robotic right now.
Yeah, full robot voice.
Sir, your form is returning.
Can you hear me now?
We can hear you, but it's robotic.
Yeah, heavily robotic to me.
We can't
Yeah.
understand anything.
Okay, now I think the
Yeah, now we can hear you.
Yes, it's okay now.
okay. I've turned off the. I was using headphones, Bluetooth headphones, so, and that's why I'm gonna try again, just one last time, okay? Okay, am I still a robot?
No,
Yes,
sir.
sir.
No.
It's understandable. Yeah.
Yes or no?
No.
Okay, so let's carry on. So yeah, why do we need L-square integrable functions for quantum mechanics? The answer is we don't know. That's what it is.
Sir, I have another question about the Klein-Gordon equation. It considers the relativity in the quantum mechanical equation, but relativity doesn't go with quantum mechanics. So what does the Klein-Gordon equation tell us?
Well, the Klein-Gordon equation is not something that can be given a probabilistic interpretation. What the Klein-Gordon equation tells us is something much more sophisticated. It tells us that it has to be interpreted as a equation for a quantum field. And then if we have an equation for a quantum field, then everything, so in a quantum field, the wave function becomes an operator. Okay, so the Klein-Gordon field becomes an operator. The Klein-Gordon wave function becomes an operator. It's not a function anymore. So the equation of continuity that we can derive from the Klein-Gordon equation, this becomes an equation which is valid for operators. Now, operators are like matrices, right? They don't have a particular value. They can have a whole spectrum of values. But just as in matrices, if you have a matrix, you can take its expectation value, right? Meaning that you can take some vector and sandwich the matrix between those vectors, right? So although this is a matrix, this is a number. So for relativistic systems which are described by the quantum field theory of Klein-Gordon equation, such an equation, the equation of continuity, can be turned into an equation for the expectation value of these operators.
So that reminds me about the continuity equation. Is this some kind of law that an equation has to satisfy?
Sorry?
Is the continuity equation some sort of
No,
criteria that?
it's an equation that we can derive from the Klein-Gordon equation, right? So what I'm trying to say is that for the Klein-Gordon equation, you can derive, when you think of it as a quantum field theory equation, you can derive an equation where instead of the rho and j, you have the expectation value of rho and expectation value of j. Now, rho is not positive definite, even in that case. But this equation then has a different interpretation. It has the interpretation that this is an equation for the conservation of electric charge, okay? So what turns out, the significance of the Klein-Gordon equation is that it describes, so the Klein-Gordon equation, describes, a system of charged spin 0 particles. Okay. So it's not a quantum mechanical equation. It's a quantum field theoretic equation. Okay. So it has more general interpretation.
Sir, I have a question about this.
Yeah.
So মানে ক্লাইন গর্ডন ইকুয়েশন ডিরাইভ করার সময় আমরা ধরছিলাম না যে v equals to 0 মানে পটেনশিয়াল,
Right.
তো এখানে মানে ক্লাইন গর্ডন describes a system of charged particles, তো পার্টিকল
They don't non-interacting. Yeah, it's a non-interacting system. So basically, for an interacting theory of Klein-Gordon equation, you will need phi. I think I'm just going to put C and H bar and everything to 0, and I think there's a minus phi, and then you can have a source term, and that source term can be lambda phi cubed or phi squared. Phi cubed term is better because it gives you a stable quantum field theoretic system. Phi squared doesn't. Okay, so these are the self-interaction term. But you can have interaction term. You can have interaction between Klein-Gordon and other fields as well. When you study quantum field theory, you will see such interactions. Okay.
Okay, sir.
So yeah, it's not going to be a complete answer, but that's my answer. Is that the continuity equation it becomes an operator equation whose expectation value tells you about charge conservation, not the conservation of probability.